on the stage of the stars you just saw, and it's now beginning to lose its outer envelope of gas, which is drifting back off into space. And that's being lit up by the radiation from the collapsing star that's left behind. Now, in this picture, we took advantage of the special filters on the new camera to isolate the light of 5 different elements, and they've been color-coded separately here. So, for example, the red in this image is nitrogen, gas, and the blue is oxygen. Now, what you're seeing here is a critical phase in what you might call galactic ecology. It's the point at which material that's been chemically processed inside of stars is returned back into space, where it can form new stars, new planets, and, in fact, life on many of those planets. In this particular kind of star, much of the carbon that is in our bodies and in other life forms is produced and recycled into the galaxy. The third picture is the only one of something outside our galaxy. It's a group of other galaxies that is called Stephan's Quintet. It's about 300 million light years away. Now, the name comes from the fact, as you can see, there are 5 bright galaxies in that field. 4 of them are actually close together in space, but the 5th one is just accidentally along the line of sight to the others. It's nearer to us, and you can tell which one that is thanks to the beautiful resolution of the camera, because it's the one in the upper left here in the picture, the blue galaxy. You can see the individual stars in that galaxy thanks to the camera. The other galaxies are 8 times farther away, and they're too far away to see the individual stars. Now, all of the blue stuff you see in this picture is young by our standards. That means it's between 10 and 100 million years old in this case. The 4 yellowish galaxies you see in the frame are gravitationally interacting with each other. They're pulling together, and you can see that material has been pulled out sort of like taffy from some of these, and there's a spray of blue stars right in the center there, which has been produced by the fact that one galaxy is running into another there. This kind of an interaction is a normal step in galaxy building, and we expect that over time, long stretches of time, those 4 galaxies will eventually merge into a single big galaxy. Now, for the last picture, we're back in our own galaxy. This is a cloud of dense material which is being bombarded by radiation, intense radiation from surrounding stars. You don't see the surrounding stars. They're out of the field, but they're bombarding the cloud in the center. And that radiation is having 2 effects. First of all, it's evaporating and even disrupting the outer parts of this cloud. And that's what produces the filamentary structure you see there, the green and the blue colors. And at the same time, the radiation is compressing the cloud and inducing new star formation inside of it. We call this triggered star formation, and it happens all the time. Now, the young stars that are being formed there you cannot see in this picture, because in this particular color band, the cloud is opaque. But if you go to the new infrared band that our camera provides, you can see inside the cloud. And so if we could go to that, this is going to be a dissolve from this picture, which is taken in the normal visible bands, to one taken in the infrared. And what you'll see is that the cloud disappears to a kind of ghost-like appearance. You see lots more stars. 4 of the bright ones in the direction of the cloud are young stars inside that cloud. And one of them, the one more or less in the center of the picture, has these jets coming out of it. You can see these beautiful long jets coming out. That's material being blasted out at very high velocity out from what's going to be probably a planetary system by the time this thing settles down. And we only see these kinds of activities in stars that are about 100,000 years old. So what you're seeing here is a very energetic infant star being formed deep inside this cloud. Now, based on these pictures and the other data we've gathered so far, we're fully confident the camera is working as it was intended to work, and we're eagerly looking forward to see what other astronomers are going to do with it over the next 5 years. And now I'll turn it over to Jim Green, who's going to tell you something about a different dimension of capability with Hubble.
Thank you, Bob. I'm going to present the first results from the Cosmic Origin Spectrograph, the other new instrument that was installed during Servicing Mission 4. The Cosmic Origin Spectrograph, we like to call it COS, doesn't take pictures in the usual sense. It's a spectrograph, and it records the spectrum of light from objects. breaking that light up into its constituent colors, much the way a prism makes a rainbow, but with much greater precision so that we can actually make quantitative evaluations of what the physics that's going on in the objects we look at. Now, because every element and every chemical compound in the universe has a unique spectral signature, it absorbs certain energies of light and doesn't interact with other energies of light. When we measure those energies of light, we can tell what chemicals are present, where they are, how hot they are, how fast they're moving, and we can see the physics of the objects that's going on, as well as the physics of the gas that the light might pass through on the way traveling towards us. As an example of this kind of observation, my first slide is a spectrum of a quasar known as Parks 0405. This object is about 7 billion light years away, and so even at the resolution of Hubble, it just looks like a dot. Okay, but it's really a giant galaxy, probably with a giant black hole in the center and millions of stars worth of material falling into that black hole, creating an enormous amount of light. But it's so far away, it's just a dot. But when we take a spectrum, which is the red line shown there, and the variations are all caused by different chemicals in the quasar and different chemicals along the line of sight towards us, we can begin to understand the physics that's going on here. For example, we've listed down there IgM filament 1 and filament 2. That stands for filaments in the intergalactic medium. We believe that most of the matter of space in the universe is actually in wispy filaments in the voids between the galaxies, but they don't make enough light to be seen by taking a picture. They have to be inferred their existence by their effect as the light travels through them, and that's what we're seeing here. And we're not only seeing hydrogen, the most common element in the universe, but we're seeing oxygen as well. And in fact, not labeled here, we also see things like carbon and nitrogen. And so the elements of life are being produced in stars like the picture we saw earlier, but they're also being distributed throughout the cosmos, and not just locally, but even into intergalactic space. And this is one of the great mysteries we have currently about understanding the cosmos, is how do these get so far away from the stars that actually produce them? Now, the great new ability of COS that we brought up here is that this spectrum was taken in less than 1/10 the time it would have previously taken with Hubble. The new instrument is 10 times more sensitive, which means we can look at 10 times as many targets, or alternatively, a target that's 1/10 as bright, and get that science. And what that means is we can start to build up a catalog of the locations of all these wisps of gas through the intergalactic medium. And instead of having a handful of such observations, we're going to have hundreds, even thousands of such observations. And we're going to be able to start to build up a map of how matter is distributed in the cosmos. And this is one of the most fundamental questions we have about the nature of the universe, is how did matter wind up structured through the universe the way it is? It started out smooth. Today it's very clumpy. It's mostly in stars and galaxies that we see. How did it get that way over the evolution of cosmic time? Now, the second image we have is a spectrum taken of a supernova remnant in the Large Magellanic Cloud. And so this is a star that exploded, and the wisp, the picture in the upper corner was taken with wide field camera 3, and the bright little rings represent outflowing gas from the exploded star. And we looked at a particular knot that we know had a lot of oxygen in it and took a spectrum of that, and we're able to actually identify then the amount of oxygen and carbon, and also it's not labeled here, but silicon in the system. And this tells us about the chemistry of how these stars explode, how the matter gets distributed between them. It even tells us about how the star operated prior to its explosion, because the explosion occurs in the winds that the star blew out beforehand. So all that interacting, we can start to understand that physics, and once again understand how did these chemicals congregate eventually into planets and life, and questions that we're all concerned about. Finally, my third image is of Markarian 817. It's a nearby active galaxy. An active galaxy means that the light coming from this galaxy is predominantly coming from something other than just the stars in the galaxy. There's more light being produced by some other physical process than by all the stars put together. And again, we assume that